It's a little sparse today, or sparse today. So we will, I mentioned last class, I will likely not be here next week. So this week's classes should kind of go on as planned, based on the information I have as of now. I'll likely be out next Tuesday for sure, and probably Thursday. So I'll have some recordings of the material that we would have covered. Once again, keep an eye on Canvas announcements. I'll convey any information I have outside of class through Canvas announcements, like I did with a problem set for extension. So I put up over the weekend. You could have turned it in to the end of the day last night. So always keep an eye out in Canvas for announcements related to this class. However, we should be kind of as normal this week. I put up the next problem set. So you can really, this is going to be a lot of interaction term stuff. So you can probably get through the first like 8 or 9 questions on it. I think there's only like 1 question related to what we're going to talk about today, which are some data issue measurement error stuff. And then I've got the next sample questions up there. I'll hold off on posting the quiz until later this afternoon. I wouldn't try to take the quiz yet. It's going to have a few more questions than the problem set does on this week's material. So if you look at like the last 3 or 4 problems, it's going to be related to stuff we talked about this week. So I would hold off on taking the quiz until after Thursday's class. But that problem set I've currently got set to be due at the end of next week. And that quiz may kind of be nicer, push the due date out a little bit further. We've got next week, but then what's after that? Thanksgiving. So I may kind of put it to be kind of give you that week as well. Hopefully you get it done before then and don't have to worry about it. But giving you a little bit of flexibility with scheduling there. That quiz due date will be a little bit further off into the future because, like I said, some of those questions we won't cover until even Thursday's class. Okay, so it's kind of where we're currently at. I'll work on getting those problem sets kind of graded this week into next week, but I'll try to get those graded as quickly as possible. Other than that, so we've got next week, which I said likely be kind of replacement videos. I'll cover the same material I would have covered in class. It's just I'll have the stuff I do up on the dot cam also recorded, which will be helpful. Other than that, so we've got that new material next week, Thanksgiving week. We then have 2 more weeks before finals week. Well, one of those weeks will be new material. It may spill over a little bit into that following week, but that week before finals really should be a lot of time in class for us to work through a practice exam, more of these practice problems, any questions you guys have, and giving us some good time to review for that final, which I forget the exact date, but it's in the syllabus. Well, I'll bring it up as we get closer to it. Okay.
I don't know if the problem set is
The 5th problem set. Am I in the right class? 729.
like it shows like if you click on it, it doesn't have the document.
Oh, I'll add those after class. So they're actually sitting. You're right, I forgot to. Oh, nope, I didn't do it for this class. I will do that after class. Thank you for saying something. Yeah, I've got the, I think I uploaded it to the other section and it must not have copied the files over. So I'll get that updated so you can kind of start working on that later today after class. Other than that, any questions for me about kind of where we're moving? Anything related to non-material? Okay. So we'll go through today. And I will start to along the way show you some things. Today will be the first day where I will try to mention what I expect you to know, and then I'll try to tell you, I'm showing you kind of what the next level would be as well. These last few weeks, I not only want to review new material and give you things that I expect you to know, but I also want to give you a glimpse into what like the next level would look like if you were to take a course after this. I think it's 470, maybe 471. I'm still learning kind of the numbers of classes. Excuse me. But for now, we'll kind of start the day off. We're really going to be talking about some of the same things we've already talked about. Right? So we have 2 forms of validity, right? Up to this point, we've really only focused on what we call internal validity. So this is whether or not the estimates that we're getting. So maybe I want to estimate for this class what attendance effect had on your exam score, right? Well, that's going to be applicable to this class, but if I have some omitted variable bias, like maybe I don't have the hours that you all studied, well, my result's not going to be valid, right? Even though I'm looking at the same kind of population, it doesn't have any internal validity because I have omitted variable bias. So that's one of the things that we've already talked about that threaten internal validity. So this is going to be something that impacts both the size of my estimate, but also maybe its statistical significance. So we've kind of talked about this, but we're putting like an actual name to it now. Now, external validity is maybe I have an unbiased estimate. Let's say I don't have any omitted variables. I don't have any heteroscedasticity, anything, right? But if I try to estimate the relationship between hours studied and performance on a test, and I use data from this class, it may not be applicable to high school students on some standardized test, right? So it's sometimes I can have an unbiased estimate, but it's not generalized. I can't apply it across several different kind of groups, right? So the biggest threats we have to kind of external validity are going to be if I have differences in population. So I can't be using regression results from a college classroom, apply it to a high school classroom. I can't take results, what did I say here, from like, the United States, if I want to know the effects of gender on wages, compare that to, I don't know, I think I had an immunity here. I think my last section I said Moldova, right? But these countries that are very different, that effect of gender on wages might look very different across very different countries, right? So my results aren't always generalized if I have differences in populations. We also could have the same subjects, but the setting matters as well, right? So the example I kind of use for this one, if I were to try to use data set from you guys on your drinking habits, and what did I choose? Ad campaigns, right? So ad campaigns on IU drinking habits, right? Alcohol consumption or alcohol company ad campaigns. I'm going to get a very different result than if I look at the effect of investing into ad campaigns at BYU. If you're not aware of BYU, I just found this out yesterday. If you are a member of the Church of Jesus Christ of Latter-day Saints, if I said that wrong, I apologize. I think that's right. You get half price tuition, right? So these are going to be very different settings, and I might have very different effects of an additional dollar spent on an alcohol ad campaign, right? So settings matter, the populations matter. Sometimes we're not going to have external validity to our results. Now, we like to, in economics, we like to find things that we can take one data set and we've controlled for enough other factors that we can get a generalized result that can then be applied to several different areas, right? But sometimes that's not going to be the case, right? So just to kind of give a basic example of this, and this one I'm not going to hammer too hard because we aren't going to talk as much about how we can solve external validity threats. They're going to be more they're going to be more intuitive that how we deal with them. And so it's a little bit outside the scope of this class. It would be much more like a research methods kind of course. But just to kind of make the point, so I have this data set and I'm going to open it up. I should have used a global, but I didn't because I was lazy. So here I'm going to copy and paste this. So I'm going to make sure I have the right file path for some of the stuff that we're going to be moving forward. Okay. So, oh, and that's the wrong file. I want to be in the data issues. I have the data issues do file open. So paste that here. Put clear just in case we run it again. And I've got this regression. So I've got some BMI and GDP data, right? So I might want to estimate what's the impact as a country has a higher GDP on that country's BMI, right? So I've got two regressions here. Now I did the natural log just to kind of make this a little bit easier, because just to kind of revisit some old things we've talked about, if I did the effects of GDP on BMI, if GDP is measured in US dollars, what's the size of that coefficient going to be? Well, it would be the effect of one more dollar of GDP. What do you think the effect size is going to be? Yeah, in fact, if we run this, and I hide the do file, 0.0000000001, right? Very, very small. So just to make the results a little bit easier to look at and also interpret just what we're doing, I'm going to use the natural log of both of those. My interpretation would be what? A 1% increase in GDP would cause my BMI to change by whatever percent that coefficient is, value that coefficient is. Now, I did a very obvious thing here, but it really goes to show like external validity threats usually are obvious, right? And we can kind of think about why we shouldn't be taking our regression results and applying them across populations or settings. So if I run the regression of GDP, trying to predict BMI, and I only do that for countries in this data set considered to be developed, right? Well, there I get an estimate that is negative. So GDP goes up by 1%, BMIs actually fall. So in developed countries, as they become wealthy and wealthier, they can be more concerned about, they're not as concerned about food security, maybe concerned more about food quality, right? Making healthier decisions. And we actually see BMIs be a little bit. Now, I've got a lot of omitted variables here, but right, that would be kind of the thought process. If I try to take this coefficient and then I try to make predictions for the BMI of third world countries, well, they have a 1% increase in GDP. I mean, they're still concerned about having enough food. Maybe I get very different results. So if instead I run that same exact regression, but I do it only for, in this data set, my developing countries, right? Not considered to be developed yet. Notice my coefficient estimate. It's no longer negative. It's now positive. Now, it's not quite statistically significant, but very close, right? And this would make sense. For developing countries, increases in GDP give people more access to food. They're going to be able to afford higher levels, and maybe we see initially BMIs go up a little bit, right? So two very different populations, I get very different coefficients, right? Same relationship, same natural logs, right? Same functional form, but different populations. So this is what we want to be concerned when we talk about external validity, that we're not trying to take one regression result and apply it to settings where it might not apply. Now, if I have the data like this, just to kind of make the point, what could I do here? If I think external validity, what we're really saying is we think the effect of GDP on BMI is going to vary across something. What do we think it's going to vary across? Whether or not it's a developed country. So what could I include that we've very recently talked about? An interaction, right? So I could do GDP and interact it with whether or not it was a developed country. Now I can kind of pick up the fact that, yeah, I'm not estimating one single effect, right? I'm estimating the effect of GDP for countries that are considered developed and also not developed. So I can do that kind of all in the same regression because I've identified if I just try to run this for one of these groups, there's no external validity. I can't apply the result from one group to another. Is that any questions on that? Is that making sense so far? So I chose this example just because we have a different sign in our coefficient. Also, it's about half the size, right? So it changed by quite a bit. Sometimes things are more generalized. So it doesn't matter if it's a developed or a developing country, an increase in my GDP might have, well, if people just feel more secure in terms of income, might they be more likely to do? Try to have children or dependents, right? So what's the effect of GDP increases on population across these two groups? So I'll run those. Well, notice there, I get coefficients that look, a lot more similar, right? This relationship, this causal relationship between GDP and population might be a little bit more generalized, right? Doesn't kind of fall victim to these threats to external validity. Okay. Any questions on this idea? I guess this one's not too complicated, I don't think. Kind of introducing this idea of external validity. All right, so if we're okay with that, we'll dive into what I think are maybe some tougher issues, which is internal validity, right? So we've already talked about some threats. So internal validity just means that the coefficient estimate I see is either going to be biased or inconsistent. So it's either going to have some bias built into it, or its statistical significance is not going to be correct, and our standard errors are going to be wrong, right? So what are some threats we talked about to this? Well, the easiest one, I think I've already mentioned it, would be if I have an important omitted variable that introduced bias. What was something else we said impacts the standard errors? There's an easy command to solve for it in Stata, but we said, it's a hard word to say. Heteroscedasticity, right? We want homoscedasticity. We have heteroscedasticity in our errors. Our standard errors are going to be messed up. Now, we've also recently talked about, well, what if I have the wrong functional form? That can cause a bias estimate, right? Where I don't have a linear relationship, it's something that's nonlinear. Or what if the effect varies across two groups? I should be including an interaction term, right? That the functional form of the regression I should be running should include an interaction term between two variables. So we've already talked about a lot of the things that threaten internal validity and are going to be causing either bias in our estimator or its statistical significance not to be correct. So what are some steps we had to addressing important omitted variables? Well, there's really two. I kind of glossed over the one, but I'll go through it here. I mean, if we have the data and I think that I run a regression, let's say my GDP BMI, I've got other variables in that data set. If I think they're important, what should I do? Add them in and see what?
See if the R-squared changes.
See if my R-squared changes. I could do some joint hypothesis test. I could also simply look at the statistical significance on the included variables coefficient, right? So that's an easy one. I reckon I talked about some of these solutions already to omitted variable bias if we have the actual data, right? Now, if we don't have the actual data, right, what can we do? Well, we actually went through methods where we can actually sign that bias, right? So just as a kind of reminder, and also a little bit more of an in-depth discussion than maybe we had at the time. So if I've got an omitted variable, the estimate I see from the regression that doesn't include it will include the true effect, but also the effect that the omitted variable would have had on my dependent variable times the covariance between the variable I included and this omitted variable divided by the variance of the variable I included. So we looked at a lot of different combinations, but I'm going to mention one in which if we can sign the bias, we're going to talk about a specific kind of bias that we aren't as worried about. So let's say I think this is like maybe an obvious relationship. I don't know, height and weight, something I know there's a positive relationship between. So if I know that the true effect is positive, and whatever this important omitted variable I have is, I go ahead and I sign this bias. If I think that my bias is also positive, what's going to be true? I'm going to see an estimate that's too what? Well, if this is the true effect, I'm adding another positive value to it, it's going to be too large, right? Or we can kind of think about it here. If the sign of the bias is the same as the sign of that actual relationship, I'm going to be overstating the effect, right? Now, in general, and a lot of other things we talked about in this class, we like to err on the side of caution, right? So what do we like to see instead of an overstatement? Well, here, let's say I had a positive effect, but I go and sign this bias and I see this important omitted variable that I have is actually causing a negative bias. And maybe I even can see that the size is relatively small. What is the fact that this bias is negative going to do to my estimate? Yeah, it's going to bring it down or push it closer to 0. So here we'd be understating. Anytime we're understating, we would kind of call this isn't technically quite correct, but just to introduce the idea, an attenuation bias. Now we can't quite say that it's an attenuation bias because that refers to the fact that it's just pushing it towards 0. What could happen if my negative bias was too large here? So let's say the effect was like 5, my bias is -10. Well, now what estimate do I see? -5. It goes to the other direction. It flips the sign. Well, that's no longer attenuation bias. It's not pushing it towards 0. It's pushing it towards a larger negative value. So with omitted variable bias, we aren't guaranteed that we're going to have attenuation bias just because the signs of our bias and the sign of the coefficient that we're concerned with don't match up, right? It could be that I have some attenuation bias, but it could also flip it. But in practice, what do we like? We like to, we know here we're going to be overstating the effect. At least here we're likely understating. Okay. Is that any questions on that idea? I don't think I went through this when we've been talking about omitted variables yet, but it kind of relates to more of what we're going to talk about today. Okay. So with this idea in mind, the size of that bias would also matter, or the magnitude. Because even if I know that I have an omitted variable, if I know that like the covariance between it and the variable I included is relatively small, I know my bias will be small. And there I just know I'm underreporting the effect by a little bit. I'm not as concerned. Right? So I already kind of walked through this idea. If you know they're both positive, well, now you just know that you're overstating the effect. Right? And you can kind of make decisions based off of that, like knowing, okay, I can use these coefficients to make predictions, but I'm likely going to be off by a little bit. Well, I won't. I was gonna say, you think about making predictions, like you could even think about if I'm trying to predict what people are going to do, maybe there are some scenarios where it's okay if I over predict. I'm not as concerned with if I over predict what they're gonna do. But we're not gonna dive too deep into these issues. Just I wanted to revisit omitted variable bias because we're gonna think about how that relates to measurement error in a second. So some things kind of that we haven't talked about yet. That's the next topic. We might even start Thursday with panel data a little bit. So some solutions we have to the omitted variable bias we haven't really talked about other than like actually getting the data or signing the bias. We have some solutions where we can actually, it doesn't matter if we don't have data on it, we can completely eliminate its effect. So instrumental variables, some strategies we call first differences in panel data that'll make more sense in the next couple of weeks. And we won't touch on this one, but I want to bring it up because I might post an announcement. I think I have an email sitting in my inbox that reminds me of this. But have any of you been a part of the economic experiments here? Yes, a couple nods. Okay, so you get paid basically to be in these economics experiments they run in a lab or a computer lab. And a lot of the times what they'll do is something like this. When you look at actual data like price quantity data to understand firm decision making, there's a lot of other things changing that impacted the price and quantity or impact supply and demand that you don't have information on. So what do we try to do in a lab? We try to have individuals make price quantity decisions like in a designed experiment where we completely eliminate those other things that we know are influencing supply and demand. It's a much more controlled setting. So we won't talk about this one because this isn't an experimental economics class. I would imagine, once again, new to the university, I'm still trying to get used to all of the courses that exist, but I would imagine there's an experimental economics course at the undergraduate level where they might dive into some of these kind of issues, right? How you use experiments to resolve some of these omitted variable bias or some of the other things we'll talk about. So one of the other things we talked about that threatens internal validity, so I won't waste too much time because we really went over it 2 weeks ago a lot, is functional form, right? If we should be including a squared term, we should be using log-log models, and all of this we said is going to cause some bias in our estimate, right? Because if we're trying to estimate a linear line when the relationship is quadratic, well, there our errors are going to, we said the expected value of our error term is not going to be 0 across different values. Our results are going to be biased. Now, one thing we haven't talked about, once again, alluding to what you would learn at kind of the next level, and I might, if we have time at the end, like one of those last weeks, show you an example of how we do it in Stata, but I'm not going to kind of test you over it. But what do we say is a problem if I want to use these like log-log models, or really even if I want to use a quadratic model? If I have what do we say? You can't take the natural log of or dependent variable if it is equal to 0. So what variables are problems? Dummy variables. Even with quadratics, how can I have a quadratic term for a dummy variable? 0 squared is 1 squared is 1, right? So I can't look at functional form for these dummy variables. We've got some different types of regressions called probit or logit that we can use to do that. Okay. Now we won't dive into them, but just kind of trying to take what we've talked about up to this point, related to what we are talking about, which is internal validity. Don't know why this isn't folding. Hold on. Come on. Let's see if I can get this to go away. There we go. So what we are going to focus a lot on today is going to be the threat to internal validity, which is measurement error. Okay. So let's say I've got something like survey data. So I think the example I used in my last section, but you can use it, whether it's like drug use data. If I get self-reported drug use data, what do you think is true about the data that I have? It's not accurate. It's probably vastly underreported, right? So anytime I'm looking at survey data, this also comes with like things like time use. You ask students how much they study, tends to be some measurement error in there, right? It's not necessarily trying to lie, but even if I'm doing it from recollection, like, oh yeah, well, I study on average, I don't know, I feel like I study like, 10 hours a week. Well, if you go back and actually log it, you're like, oh, I only study 6 hours a week, right? Like, so there might be some like not what we call intentional like lying, right? But we're gonna have some misreporting of the data. Well, I don't actually ever observe some of these values. I only observe what is self-reported to me. Self-reported physical or mental health, right? Is another one that we often see a lot of measurement error in. So when we look at our data set, we're gonna say what we actually see is this X tilde. This is the self-reported, and it doesn't have to be self-reported. I'll talk about in a second example where it wouldn't be, but just for now to think of it. When you have self-reported data, you only observe what the person self-reports. Now that X tilde will include the true value, whatever your self-reported drug use is. You have an actual drug use, right? But there's going to be some error between those two, right? That the self-reported amount is going to be different than the actual amount. We're going to call this, I just call it error here, but it's essentially measurement error, right? Excuse me. So we have like the typical error that exists in a regression equation. This error, this is our measurement error in the X value or our independent variable. So we can kind of rewrite our regression equation to look something like this. Right? We're going to have the effect here of X tilde, right? So it gets kind of weird to think about. I really didn't change anything here. So all I did was take the actual regression I want was beta 1x, but we don't observe beta 1x. I know that x would be equal to what? X tilde minus the error term. I rearranged some things a little bit. And you can rewrite your regression equation as you'll find the effect of the self-reported value, but there's also going to be an effect that comes from the part that wasn't reported, right? Like just because they didn't report it to you, it's still going to have an impact on y. But you don't actually get to observe this measurement error. All you observe is this. But this is what the actual regression equation should be. It should include, like, how is y changing? Y is changing by not only the part that they report to you, but it's also impacted by the part that they don't report. Okay? So if I simply run this regression, it's almost like my error term now has the original error between my y and my predicted y values, but it also has the effect of the measurement error that I didn't have data on. So if I'm not including this in my regression, it becomes part of my error term. If I leave out the measurement error, what is that kind of like? So if I leave out something that matters in predicting y, I have an important omitted variable. Our measurement error is, it's not one-to-one, but it's essentially like we have an omitted variable, right? So we now kind of call this u, it's like our composite error term. When we make predictions for y, we're going to only be able to make them based off of the self-reported values for x. So our errors are going to be a lot larger, right? And they're going to include the effect of what that measurement error would have been if we had data on it. So this is going to go against one of our kind of assumptions, which is we said, okay, I need, right? Well, it could go against one of our assumptions, which is that this composite error, right? For different values of self-reported, whatever it is, the expected value of our error term needs to be 0. It might not be now, right? Because you can think about, let's say we had drug use, right? I observed the self-reported drug use data. Well, maybe for people who report I think I didn't put an example up here. I'll do a really basic one. Let's say I was wanted to know, well, the drug use one works. And then I have another example later on. People that use a higher level, what do you think is going to be true about how much they underreport their drug use relative to someone who like hardly uses any? Or if it's when you drug use, think about I asked you all about your alcohol consumption. If you're drinking 100 drinks a week, are you going to tell me that? Probably not. You're probably going to, even if you don't care that I know that you drink a lot, you're going to be like, I don't know. 30 drinks, 30 drinks a week. I don't know what it is, whatever it is. Well, what if you only have 2 or 3 drinks a week? You're probably going to report, as long as you're over 21, 2 or 3 drinks a week, right? You're not as concerned. I mean, that's not, I wouldn't say an embarrassing amount, but like, that's not an amount that I'm going to be concerned with if I see it. So what's true about my measurement error there? When alcohol consumption is high, my measurement error is very large. When my alcohol consumption was low, measurement error is going to be relatively small. So if my composite error, the measurement error, which includes the measurement error, if it depends on the actual values of the x variable, now I'm going to have now I'm going to have a bias estimator, right? So we'll touch this in a second. This would be kind of what we call non-classical measurement error. So I've got this laid out here a little bit more in just a second. But I want to think a little bit harder about what this measurement error is doing. So this should be the actual regression. If we had the actual data for X, like this would be your actual alcohol consumption, so to speak. Well, I can rewrite that as that's just going to be the same as the self-reported amount minus the error term. Okay. I'm then going to kind of distribute that coefficient. So I get this regression where it's going to be X tilde, but also this coefficient times the measurement error. I'm just distributing things here. Well, that error ends up in my composite error, right? So this is the actual regression I run with the self-reported values. So that's kind of where we left off kind of in the last slide, just rewriting in a slightly different way to get there. So if we're using only these self-reported values or the values that have measurement error built into them, our estimate's going to be biased and we can prove why, right? So I'm going to walk left to right here. If I have this measurement error that I'm not including, the effect that I see, so the actual coefficient estimate I see from my regression results will include the true effect, but it's also going to include how my error is related to the variables I included. So before, when we just had a simple error term, the difference between y and a predicted y, remember we said that that error can't depend on the values of X, right? Now, if it did, we would have had some bias, and we didn't dive into what that bias would be, but that it would bias our results. We needed that error term in the original, we had the actual data to not be related to the values of X. So we need the same thing here, but it's now not just the error term that can't be related to the X values, it's our composite error, which includes both the regular error that we would have, but also now our measurement error. So usually, all we had here was like the covariance of X with the error, that was always 0. So this always went away, right? But now, it's the covariance of the self-reported X values with our composite error. So, usually, right, this kind of covariance of our, where is it? Yeah, covariance of the X values with the actual like original error term we have in every regression, this is always typically 0 for us, right? So if I'm thinking about the covariance of the self-reported X with our error term, that's just 0, that would go away, right? What am I still left with? Well, I still have the covariance of the self-reported X with my measurement error. So I'm just going to rewrite X tilde, we said was just, that's self-reported, so it's the actual X plus the error term. So I now have here, okay, what's the covariance of my X values with the error term? So here we're going to make one more assumption. So the assumption here is that we have what we call classical measurement error. That unlike the example I used with drug use, that the values of X will not influence how much the measurement error is. So I'll give you what I think is a decent example of this. If you ask people to self-report their income, right? They're not trying to lie to you, right? But no one knows exactly what their pay stub is down to the cent, right? So if I ask you how much, about I think 51,000. Look at there. Oh, you actually made $52,134 last year. Okay. Well, I think I made 85,000. Well, you actually made 83,000. So it doesn't matter what level of income you make. You're probably just going to anchor to like a close round number. The measurement error there doesn't depend on the value of income. It's just completely random. So if the error, the measurement error doesn't depend on the values of income or that X variable, well there, this covariance between X and our error term, that would go away as well. Right? So now all we're left with is the covariance of the error, measurement error with itself, but we had that coefficient up front. Well, the covariance of anything with itself, that's just the variance, right? So we end up with the variance of our error term over, and here I was just rewriting the self-reported values we see, or the actual values plus the error term. Well, remember, there's no covariance. If we like, you go back and like, 370, if you can't like the variance of X plus something isn't the variance of this plus, it's the variance of this plus the variance of this. Plus the covariance. Well, there is no covariance here, right? So we can actually just separate these out to be the variance of the actual X values and the variance of that measurement error. Okay? Once again, I'm not going to make you work through all this. I'm just kind of showing you where, giving you the mathematical support behind where it comes from. Well, now that I have this, right, I can rewrite this. Well, there's a constant in both of this, so I'm just going to pull that out front. I now have 1 minus this. I'm going to just rewrite this a little bit, right? 1 would be this divided by itself, do a little bit of math. What I can end up with is that the estimate I see when I use the independent variable that has measurement error in it, as long as it's classical measurement error, where the measurement error does not depend on the values of X, right? This is the income example. People just anchor to the closest value, right? There's no, doesn't depend on their level of income. They're just going to be a little bit off. If I ask you how much money you spent this week on, I don't know, food, no one's going to get it exactly right, right? And we're all going to be off, the amount we're off, probably just random. Doesn't matter if I spent $100 this week on food or 50, right? I'm going to tell you an amount that's probably not quite right. So the estimate we see using the self-reported values, X tilde, will be the true effect times this fraction. What's that fraction always going to be less than? If I take the variance of X and I divide it by the variance of X plus the variance of something else, well, variances are always positive. So that denominator will always be larger, positive, but larger, right? I've got the variance of X divided by the variance of X plus some other value. That fraction will always be less than 1. So the estimate that I will see if I run a regression with a variable that has measurement error in it, that's classical measurement error, I'll always find the true effect, but it's going to be a little bit lower, right? Or it's going to have attenuation bias. Now here we know it's attenuation bias because variances can't be negative. So the very lowest this fraction could ever be is, not technically, but it's going to, in the limit, approach 0. So the lowest I could ever see is 0. I can't see it flip signs. Here I know that when I have measurement error in my independent variable, I'm only going to have attenuation bias. It's just going to give me a smaller in magnitude estimate. Okay? Any questions over this before we keep moving here? Okay. All right, I think the next slide do I have? I think I probably already mentioned, I haven't mentioned all this, so I want to hit this before I show you some other things. So we already just talked through this, that we have this attenuation bias. It's just going to push it towards 0. It didn't go through this though. What if we have no measurement error? What's true about the coefficient that we'll see? Well, if the measurement error doesn't exist, the variance is going to be 0. So what would that fraction be? 1. So the estimate I see will actually be the true effect. Right? So if we have no measurement error, this kind of proves that we'll have an unbiased estimator. Now, as I start to have higher and higher measurement error, what's going to happen? Well, we've got, this is going to be the estimate we see. It'll be the true estimate times the variance of our X variable over the variance of our X variable plus the variance of our measurement error. So just to kind of give, it's a little more sensitive sometimes. Let's say that the variance, well, do 2 things. Let's say this was the variance of our X variable was 10, and the variance of our measurement error was also 10. What's going to happen to the estimate we see? Well, it's going to be the true effect times what? 1/2, right? So this is going to be the estimate that we see, and I'll kind of call this small variance or a small variation in the measurement error we see. What happens if all of a sudden this measurement error, like when people self-report income, what if they're really bad at it, right? So they're like rounding to the nearest 10,000, right? Or they're not. So let's say this is something like, what makes this nice and easy for me? Let's say this was instead 90. So if I think about what is the estimate I'm gonna see if I have really large measurement error? Well, now it's gonna be what? Beta 1 times what? 100 or 10 over 100, so 1/10. So notice the larger the measurement error's variation, the closer my estimate is going to be to 0. So I'm not as concerned with measurement error if it's relatively small. So this is like really with like income, not gonna be that large really, right? You know, if the measurement error starts to become really large, like, I don't know, maybe I have a device that's really bad at reading. So if you look at some of the data from like a CVS, let's just say they recorded it, all those blood pressure machines that you put like your arm in, they're actually terrible. Like if you look at the measurement error, like on them, they're not accurate at all. I shouldn't say at all. They have a wide range, a wide confidence interval, essentially, right? So if I look at that data, it's gonna have a really wide variance. My estimates are gonna be a lot closer to 0 or something like that. Now, I should also point out, it's not just the size of the measurement error that exists. Because when I'm looking at something like income, the measurement error, the variance could be relatively high, but it's not just does the measurement error have a high variance, it's a high variance relative to the variance of the variable you're looking at. So yes, the measurement error will have a high variance for income, but the variance for income is going to be relatively large as well. What is this fraction going to be a lot closer to? 1,000 over 1,090 is going to be a lot closer to 1. I'm not getting as much attenuation bias. So the size of your measurement error's variation does matter, but it's more about the size of its variation relative to the variation that exists in that X variable. Okay? Any questions on this idea here? So really want to focus on the difference between small and large, but it is important to think about the size of your measurement error, the size of your measurement error's variance relative to the variance of the actual X variable. That matters as well, right? Okay. Questions? Yeah.
So just to make sure, the
Yeah.
closer we are to 1, the more accurate we are, right?
Yep.
Okay.
Yep. So the closer, yeah, the higher that measurement error gets, right? The further that fraction gets away from 1, we're now getting estimates that are closer to 0, further away from what that true effect should be. Okay. Excuse me. All right. Okay with that for right now? Okay. So let's jump over to Stata. Oh, we'll talk about this later on. We have ways of addressing this. We won't talk about them yet, but one of the topics we're going to cover the rest of the semester is going to be instrumental variables, and then some maybe advanced techniques I'll mention once we get there as well. So before we go to Stata, we just talked about classical measurement error. That's probably going to be a lot more of the questions that I'll ask you about, and we'll kind of see why, I think, as we work through practice problems and we work through stuff this week. But let's say we had non-classical measurement error. So when I was working through all that mathematical proof, it really hinged on the fact that the measurement error didn't depend on X. Let's say that the measurement error does depend on X, so the covariance is something other than 0. So I think I've got an example here. Well, so before I go to the example, if we have non-classical measurement error, where the measurement error depends on the value of the X variable itself, our estimates, we don't know what's going to happen. They could go up, they could go down, they could go up by a lot, they could go down by a little, they could go up by a little, down by a lot. We don't know, right? They could flip signs. However, I could give you an example of when this non-classical measurement error exists. So we think about like self-reported intelligence. If I ask all of you how smart you are, you will vastly underreport how intelligent. First of all, you're at a D1, like Big 10 university. Automatically, you just put yourself above the majority of the population, right? You've made it this far. So so that once again, you're in, look, I don't know what percent of the population even knows what the word econometrics means, but it's not a very large percent, right? And so automatically, like you probably, but you'll be here like, I don't know anything, right? So if I asked you to, like, on a scale of 0 to 100, report your intelligence, college students on average, they'll underreport by a lot. People who are intelligent, they know how much they don't know, right? And so knowing how much you don't know, you think you're a lot less intelligent than you are. Right? So your measurement error, when intelligence is high, you've got pretty big underreporting. Now, I have a neighbor, really nice guy, but he's got, 5 cars that don't look like they've been driven in 30 years on his property. He's got like an old electric utility, like the things they send people up in that just sits there. It looks, it's all overgrown. It's a relatively small. He's not the brightest guy in the world. He thinks he knows everything if you talk to him. Like he thinks that he knows how the government should run. Right? So when you look at people of lower intelligence, they don't even know what they don't know. Right? Even someone of moderate intelligence will think that they're really smart. I understand these issues. I watch the YouTube videos. Right? So the self-reported intelligence is definitely correlated with what their level of intelligence is. Our measurement error is not classical. It's not random. Right? It's not just like I'm trying to remember how much income I make and I'm off by a little bit. No, the way that I'm going to report my own intelligence depends on what my underlying intelligence is. If we got non-classical measurement error, we don't know what's going to happen to the coefficients, right? So hopefully I can give you a little bit more insight as to why. So kind of jump back into Stata here. So the first thing that we'll kind of work through, we'll take a step back and we'll think about classical measurement error. Excuse me. So I'm actually going to change this from the original file I had just to save us. Well, no, I'm not, because I have the values in here. So let's reopen that data set just to make sure we're starting anew. I'm going to scale that GDP variable. This is simply to make the coefficients easier to look at. Okay. I'm then going to run my regression with the actual BMI values. And then I'm going to do something where I'm setting the seed. I'll mention more about this in a second. Right? So I run this regression. I get the effective BMI on predicted GDP is about 60,000 here. We're not going to focus too much on the interpretation, just the actual value. Let's say instead, my BMI values in this data set had some measurement error in them. Well, I'm going to artificially create that measurement error so we can see if what I'm saying is true, right? So I'm going to create this variable, which is just a random variable between -1 and 1. It's just going to be a completely random measurement error. So this should be what type of measurement error? Classical, right? So I'm then going to create a new variable, which is the actual X value, BMI, but includes this measurement error, okay? So I'm going to go ahead and do that. I'm now going to run a regression where I'm using not the actual BMI, but the BMI variable that had the measurement error. Well, what should happen to my estimate? If it's classical measurement error, we said our coefficients should be attenuated or smaller, closer towards 0. So I go ahead and run this. Sure enough, get about 54,000 here. Okay. All right. Now, when I talked about that equation that was going to hold, like how much our attenuation bias would be, you might originally think, oh, well, I've got the actual data. What I could do is actually, if I know that I just saw like what, it was like 54,000-ish. Let's say I didn't have the actual BMI variable, but somehow I know from a different data set what the variance in BMI looks like. I have the variance of BMI. I created that measurement error, so I kind of know what its variance would be. If I had values here, I could plug them in and like back out what the true effect should be. Now, the problem with doing this in the example that I just did, and I think we'll have enough time to get to where this won't be the issue, I only did this with one set of random numbers. Really, in order to know what coefficient estimate I'm going to see from that measurement error, I would need to have this thought experiment with like 1,000 different samples of 1,000 different sets of random numbers. But we're going to work our way towards that. But that's the general idea. I can take the estimate that I see from my regression. If I know that classical measurement error exists, if I can get a good idea, even if it's not from my data set, but from somebody else's data set, what the variance on BMI and what the variance on this measurement error might look like, I can get a rough idea about what the true effect should be. right? Because now it's just, once I have values for this, one equation, one unknown. Okay. So we'll kind of revisit that here in just a second. But for now, I want to kind of make a data point for something we already talked about. So I've got this second measurement error I'm going to create. I'm going to call it measurement error big. It's going to be coming from a uniform distribution, so still completely random. But notice the numbers that it can be between much wider. So what should be happening to my variance of the measurement error? It's going up, right? So if the variance on my measurement error is, wish I had two strings in this class, larger. If my denominator is larger, what's happening to this fraction? Guys, if you divide by a larger number, it's getting smaller. If I multiply by a smaller number, what's happening to the coefficient I see? Getting closer to zero. So when I look at this second random measurement error, if I then create a BMI variable that includes not the small measurement error, but the much larger measurement error, and then I run a regression using that, my estimate should be even smaller. I'll go ahead and do that. Sure enough, now it's all the way down to 7,000. Okay? So you can see as that measurement error increases, that variation of my measurement error increases, I'm getting a much smaller estimate. Okay. Any questions on that before we continue here? So I don't know. I can tell you these things and we work through the math, but I don't know. For me, what always made sense is like seeing it play out in the data. And you can, like I said, here we're like artificially creating measurement error, so we can see what's going to happen. Now, what if I had non-classical measurement error? Well, we said there all bets are off. We don't know if it's going to be closer to zero, it could be larger. How much closer is it to zero? So here, I've got an example where I'm going to create some measurement error, and it's going to be a function of what the actual BMI values are. So it's going to be this, random measurement error, but then plus this second component where it's 0.1 times BMI. So this is like a very egregious way of making sure my measurement error definitely depends on the X value, right? Excuse me. So if I do that, then I create the BMI that includes this new measurement error. My estimate could be higher, could be lower. Okay, it's a little bit lower than 60,000, right? But what if that measurement error was not random plus 0.1 times BMI? What if it was random minus 0.2 times BMI? Well, now here, will my estimate be too large or too low? Well, now my coefficient is larger than 60,000. So I don't know anything about the covariance or what relationship exists between BMI. Here I do because I'm artificially creating it. But in practice, we don't know. If we have non-classical measurement error, it could cause my estimates to be too high, could cause them to be too low. You could even have some weird ones where it's like random, but multiplied by instead of added. Here I see, okay, not only is it lower, now it's even lower, right? But these get a lot harder to sign, right? These get a lot harder. In fact, I think I've got another one here just to prove the point. And these are all, don't worry too much about what I'm just doing different relationships, right? Different types of relationships between BMI and the measurement error. Notice you can actually get here, the sign flips. So with non-classical measurement error, we can't guarantee attenuation bias. The coefficient could be higher, could be closer to zero, but just like omitted variable bias, could actually flip the sign. Not only could it flip the sign, what does non-classical measurement error do? What's happening to our p-values? Well, sometimes they're statistically significant, like here. Sometimes they're not as statistically significant. Sometimes they're, where is that? Yeah, really not statistically significant, right? So I can't really say what's going to be happening to that bias or the consistency of my estimate if I've got non-classical measurement error. Okay. Any questions on this before we keep going? I got something else I'll show you here. And just to give like a little bit more of a practical explanation. Okay, so what the hell do I do? Right? I know that I don't have the right variable, it has measurement error. Well, maybe I can find other data sets that can determine what the covariance is between measurement error. So you'll have a lot of some of these economic experiments, they'll they'll gather self-reported data, even though they actually have the actual data. That way they can get an idea about how this measurement error is related to that X variable. So they might have something like, I know like that, there's a couple data sets where you have like IRS data, and then you have like self-reported expenditures, or you have self-reported like how much you paid in taxes, and they never line up perfectly. When you have the actual X values, you have the self-reported, you can get an idea about what that covariance looks like and whether or not you do have classical or non-classical measurement error. Okay. For the sake of problems and things like this in this class, I will tell you that you have classical measurement error. Okay, so the next thing that we're going to cover for the rest of the class is this same idea, these same concepts, just in a slightly different way, and hopefully prove you a little bit more than just these other ones I did. So I'm going to push you a little bit further than I would ask you questions on, but I'll try to mention things that I would expect you to know as we go through this. So first of all, I was lazy and didn't use my global. So I'm going to go through and copy and paste where this actual, and I don't have this up on Canvas, but I'll upload it after class. So I just got to make sure I'm using the right file path here. It's the same life expectancy data, but I need to make sure I'm using the right one. Oh yeah. Yeah, that's next class. So we got enough going. All right. So what I can do, so I mentioned before, when I run this regression with the measurement error variable, I'm only seeing one coefficient, right? It was from one set of random numbers. Really, in order to prove to myself what the coefficient estimate I will see would be with the measurement error, on average, I should have like 1,000 different random numbers that I'm estimating that coefficient from. Okay. So when I was setting that seed earlier, that was one of the lines of code. What that guaranteed is that everybody who's running this code, so the way that, honestly, I kind of understand how it works. I'm not like the best computer programmer. I'm not a computer programmer. I can program in statistical programs, but what essentially it's doing is you have to have some starting value to generate random numbers. And what Stata will do, unless you tell it otherwise, it'll always randomize the start point, so that you randomize the start point, you're always then getting a different set of random numbers. If you set the seed, you're telling it start with the same starting point. So then you're guaranteed to get the same set of random numbers. I didn't set my seed here at all. I'm just letting it, Stata kind of randomly choose the seed to be different values. So I'm getting completely different sets of random numbers. So what I can do in Stata is define what we call like a function. So, or I guess they call it a program. I've always referenced it as a function, but the actual syntax is program. You kind of notice it like tells you all of this is part of the program, right? Start here, call it my reg, right? Run all of these lines of code, and then end the program. So this is basically what we just did. I dropped all here just to make sure I didn't have any variables still existing. I opened up the data set. I scaled the GDP variable so we can compare to that 60,000 that we were looking at earlier. I generated a random measurement error. Now here, just for some things we'll talk about in a second, I made it a little bit easier. I was pulling from I was wanting random numbers, but instead of uniform, I did a normal distribution. Because that way I can guarantee the mean of this random numbers is 0. But I also wanted to know what the standard deviation was, and it's a little bit easier to see it here because that's just 1. Right? I tell it what the standard deviation is. If I know the standard deviation, I know the variance has to be 1, right? 1 squared is 1. I then created my new BMI variable that had the measurement error in it. That's just like we were doing before. I run the regression. I then have this command outside of my program that says, run this simulation using my program, myreg. So go through and do this 100 times. So it's going to go through, randomly generate numbers 100 different times, and then save the coefficient estimates and their standard errors. So I'm basically going to have 100 different values from 100 different sets of random numbers about what those coefficient estimates would be. Now, if I look at the average across those 100 different regressions, that's telling me what coefficient I would see if I had this measurement error involved. It's not just picking kind of one. It's the same idea. Like if I had, we were saying, if I took a random sample of 1,000 people, I'm gonna see an average income of maybe 54,000. If I take another random 1,000, I might see 55. Another random, 55,259. Well, how do I know what the true average income is? If I have 1,000 different samples, I look at the sample of those sample means. Same kind of idea here. We're gonna look at the average or the mean of our sample coefficients. So I'm gonna run this, right? And then just kind of summarize what those 100 different coefficients are. Oh, but I have not yet. Here we go. I need to run my program first. Now notice when I'm just defining the program, nothing happens here. I'm then gonna go to simulate this. Takes a little bit of time. So I now end up with the mean across these 100 different samples, where I have 100 different random measurement errors created. On average, I'm getting a coefficient estimate of 50,364. Okay, so I'll write this down before we go. So I've got. Bear with me, I'll switch over here in just a second. Oops. BMI. So one of the other things that we needed in that equation where we were determining what our attenuation bias was. So this is essentially going to be the estimate that we see on average if we use this BMI variable that has the measurement error in it. Right? We could also say, well, I've got the actual BMI values. Whoops. Oh, because I need to open this data set back up. Give me 1 second. If I go back to the original data, what was just to make this easy, variance on my BMI was what? 4.8132, right? So 4.8312 was the variance on our X variable BMI. We know the variance on our measurement error because if the standard deviation is 1 squared is 1, right? So here was our equation that we had. There we go. The estimate we saw here, we just said from 100 different random samples was 50,000 something. There we go. 50,364.57. I found the variance of the actual BMI. My measurement error, we said had a variance of 1. I could back out what this should be, right? So I'm going to open Excel here and do the math as we talk through it. But if I had what, 4.8312 divided by 4.8312 plus 1, that fraction ends up being 0.8285 approximately. I think 1, even if I go 1 more. So now I've got, well, what is the true effect of BMI? Well, I could just divide both of these by 0.8285, and it should tell me, what did I do here? I missed something. There we go, 851. That should tell me what the true effect is, right? So if I go ahead and do this. Here was that 0.82. We said take the estimate we saw of 50,364.57 divided by, okay, that value. Okay, I'm not quite there. It's 60,789. What was the original one we had? I think it was, well, there it is. Nope. We're all the way back up here. Hold on. 60,088. It's not quite right. Well, here, what's, huh?
I think you swapped some of the numbers when you were multiplying. It was like 4.312. No,
Oh. In here?
it was when you were writing it, you wrote I think it was 132, you were 312 or something like that, so that's probably why.
4.8312. So let's see, did I write the variance down wrong? 4.8. Oh, yeah, so that might, that might do it, but that isn't the only thing that did it, but thank you for catching that.
Mhm.
So I did what, I switched these around. 1.3. 1.3. So we're getting a little bit closer, right? I think the actual value we had up here was what? 60,088. I'm a little bit off here, right? What could account for this? Rounding is going to be a part of it. Like I'm rounding pretty egregiously here, but also it's going to be close. But I only did 100 random samples. Truly, to get that to definitely be equal, I would need, in theory, an infinite number of random samples. I could do this for 1,000, and I thought about doing it for this class, but well, it just takes a really long time for it to run. So it's going to be a really long time. But you can kind of hopefully see here, it's really close. Like that idea is going to hold if we could theoretically get an infinite number of samples. Okay. Excuse me. So where are we at in this code? Because I know there's one more thing I want to get through. Nope, not here. What were we just looking at? Oh, right here. So hopefully, I don't know. I wanted to do this to kind of show you like, hey, I'm not going to expect you to do this on the problem set or anything like that. But it's starting to show you like the power that Stata has. Like we can start to create these programs, run tons of simulations. And you know, it becomes pretty powerful. Now, what I would expect you to know is the next concept we'll talk about. So let's say I do this exact same thing, right? So I'm going to now go through down here, because this was just kind of all the math that I was kind of doing in Excel. So I'll post this so you can kind of go back and look at that. I'm going to create a second program, which is the same thing, but I'm now going to be generating my measurement error from a distribution that has a mean 0, standard deviation of 10. So the variance is going to be higher. So if I do the same thing now, and I take 100 different sets of random numbers, what should be true about that mean coefficient estimate that I see? It's not going to be 50,000, it's going to be, so if we go back, if my measurement error is now, actually, it's not 10 because that's a standard deviation. I need the variance, so it's now 100. So this went way up. What's going to happen to my fraction? So what's going to happen to the estimates that I see? And go way down, right? And I can prove this to myself, not just from my, like, it's not like I cherry picked the random numbers earlier by setting that seed. I could have done that, but I didn't, right? What you can actually see here now is if I have this second program, which has this larger variance, now when I run that simulation and I look at the average coefficient, I should hopefully see something a lot smaller. Well, I went from a variance of 1 to a variance of 100. It should dramatically decrease that coefficient I see. Questions on that before we keep moving here? Okay. Now I didn't, well, first of all, I don't want to do it. Sure, there's no questions. Okay. So we'll try to do one more thing here. It might get mad at me. I think I need to clear programs. Yeah.
I have one question.
Yeah.
Can you explain when you say the simulation, the
Yep.
_B_SE regress, can you explain like?
Yeah, so it's just running this code, which generates a new set of random numbers every time, and then saves what the coefficient estimate was from this regression, and saving the standard errors. That's going to be something we're not really using today. I'm going to use it next class.
I see.
Right?
Okay.
And then do that 100 times. This is where I could change this to 1,000,
Okay.
and we could just sit and watch it go like this for forever.
Yeah.
But yeah, that's what that line is doing.
Okay. Makes sense.
So let's say instead, I generate a measurement error. I'm not even sure it'll let me do this. I think it will. It might freak out, but if not, I can do something different. Well, here we go. let's just say I generate measurement error, that is 0. So it has no variance. In fact, it doesn't even have to be 0. What if it was just 5? Well, the variance on my measurement error would still be, so let's say everybody underreports, or sorry, everyone gets the same exact measurement error when they self-report income or alcohol use or whatever it is, right? Well, my measurement error has a variance now of 0. What should be true about the coefficient estimate that we see? Well, if this is 0, what would this fraction be? So if I have, let's just say 10 over 10 plus 0, my fraction is now 1, right? So what should my coefficient estimate be? The true effect. We can actually prove this to ourselves here. If it lets me redefine this program, which I think I've got the right syntax here. Sure enough, what estimate do I get? That's 60,088. Right? Now you could also do a very similar thing. So is everyone clear what I just did? It's like a thought. I mean, this would be like, this is also kind of highlights the measurement error doesn't matter unless it varies across individuals. Because let's say everybody in the data set was confused. Let's say I was like recording something and I asked you about what I don't know, what year is it? For whatever reason. And I did it in a really weird way. I'm like, okay, well, yeah, but once the year is halfway past, it's almost like you're in the next year. So what year is it? And you're like, oh, well, so should I be saying 2025? Like, I mean, everyone's like, oh yeah, I guess that's a weird way of saying it. Well, no, I actually wanted you to say 2024. Well, everyone's going to have the same measurement error. There's no variation. Doesn't matter, right? We have an unbiased estimate. So the only thing that measurement error, the only place where that bias is coming from is the fact that if we have variation in what that measurement error is, okay? Or if it's not like constant across every person, basically. You can also do a weird thought experiment. So let's say instead of here, let's do the normal one again. And let's do something like egregious. I'm going to create a massive variance. What should this drive my estimate really close to? 0. So we run this. Yeah, 0.00000004. So just kind of highlight, I always like to do these thought experiments with data and things because it kind of proves to me like those, I don't have to go through like all the mathematical proofs, kind of is showing me that yes, these things will hold, right? All right. Any other questions or anything there? All right, so that's all I have for today. We'll kind of pick up on doing a couple more measurement errors, some other data issues on Thursday. I might introduce the idea of panel data, because I think we'll have enough time. That'll be the next topic we go through is panel data. Then after Thanksgiving, we'll go through instrumental variables, week of review, we're at final exam, right? So have a fun, safe afternoon. I will see you guys on Thursday.